is Rushang Karia. He will talk about how we can use featured learning for planning, introducing an interesting new approach called leapfrogging. Go ahead.
Hey, can you guys hear me clearly?
Yeah.
All right. Sorry. All right. Hello. Hi, guys. Thank you for organizing this workshop and giving me an opportunity to speak. My name is Rushang, and I'll be presenting our work on learning generalized relational heuristic networks for model-agnostic planning. And this is joint work with Siddharth Srivastava of Arizona State University. So the first, I would like to begin by asking what is planning. So planning is basically giving an initial state and a goal condition. The standard notion is to find a sequence of actions that satisfies the goal condition. I come from the classical planning literature, where the question is, how do we represent a state? One of the notions in classical planning is to use relational representations, where a state is represented as a conjunction of Boolean predicates. So for this example, robot at XY would imply the robot X is at shop Y. One of the open questions in planning is that planning is pretty hard. Between problem 1 and problem 2 over here, the problem 1 just has 1 spanner and problem 2 has 12 spanners. Even though the plan is relatively trivial, where the human or the agent just has to pick up the number of spanners and get to the warehouse, there is a combinatorial explosion of the state space, whereas problem 1 has only 6 states, problem 2 has 8.1 million states approximately. Another issue with planning is that planning problems usually have very long horizons with very sparse rewards, because the reward signal is only obtained when you reach the goal state. And this makes it difficult for reinforcement learning or other general search techniques to do planning. So the classical approach to solving planning problems efficiently has been heuristics, where given a state and a goal, the heuristic value of a state is the estimated cost to the goal from that state. And certain kinds of functions known as heuristic generating functions can synthesize heuristics, but at present they require action models as input to themselves. Heuristic generating functions are beneficial because they often allow planners to solve problems very efficiently and very fast while expending very less effort. And they're often applicable for any domain which is written with the underlying representational language. However, the HGF itself often needs to be hand-coded by domain experts, and it cannot be easily transferred when the underlying representation changes, meaning a new domain expert has to sit down and write a new HGF for that representation. So the big question is, can we learn to plan? And deep learning has been proposed as an approach for learning to plan. However, there are several challenges when using deep learning for planning, and I'll be going over some of these challenges in the next few slides. So the first challenge is learning across different problem instances. What I mean by that is that if you look at problems 1 and 2, we can see that the heuristic value is the same. However, the problem 2 uses different colors, which means it has different names of objects. It has different shop, possibly Ace Hardware. So both states are fundamentally the same, but the object names are different. And a learner would have to be able to reason between these two states at a higher level of representation that ignores low-level features like the object names. Another problem is where there are common patterns to the solution, where, for example, for problem 2, where there are 2 spanners, the policy would just be to run a loop collecting all the required spanners and then moving to the warehouse once the required number of spanners have been collected. And this leads to a desirable property for learning heuristics, which is generalizability, where we can learn to transfer heuristics across different tasks independent of the object names and numbers. The second challenge is learning across different problem representations. The transition function for this problem could be specified by a successor function, an explicit transition table, or a black box simulator. So a model-agnostic learning method would be able to learn a heuristic for this problem independent of whichever underlying representation was used. The final challenge is learning when generating training data can be arbitrarily expensive. Generally, solving problems using heuristic search is relatively cheap, but solving problems blindly is very expensive. However, in the case where heuristics are not available because action models have changed, we are forced to use blind search. And in these settings, generating training data can become expensive even for relatively few problems, which undermines the overall utility of learning itself. So another property that we desire our learning approach to have is data efficient learning, where we can learn heuristics even in the absence of training data. And if we combine these three properties, we reach relational meta learning, which can help in effective model agnostic few shot learning. And indeed, there has been a ton of related work in the area. For example, strips HGNs utilize graph neural networks to achieve generalizable heuristics. However, they need access to action models and training data. Generalized reactive policies, they can learn heuristics independent of training data with just a problem generator. However, they need domain experts for custom provided input representations. Meanwhile, bootstrap learning also can learn heuristics in the absence of training data and for any representation. However, the heuristics learned cannot transfer to any other problems. So our approach, we propose generalized heuristic networks as a domain-independent paradigm for synthesizing domain-wide heuristics. And we are model agnostic in the sense that we do not require any information about the action models or transition function. We do require a relational representation for the state representation. So we achieve generalizability by using state abstraction to abstract away any problem-specific features. So in this example, there is a robot and a bunch of rooms, and there's a gold bar in one of the rooms and a robot in one of the rooms. So we use abstraction in which the empty rooms get mapped to a single abstract state. And similarly, we can abstract away information like different object names, which is by the different robots icons, and we can have them mapped to the same robot icon. We are model agnostic in the sense that we propose an abstraction encoding scheme that sits in between the state representation and the neural network, so that any external representation could be used as long as the encoding scheme can convert it into the desired representation. And finally, we develop and evaluate leapfrogging, which is a method proposed by my co-author in joint work with Groshev in 2018 as a few-shot learning method. So the first objective is to make learning heuristics generalizable. And we do this using canonical abstraction, where groups of concrete states are grouped into an abstract state by means of abstraction predicates. And using abstraction, object names and quantities are abstracted away while retaining expressiveness of the state that allows for efficient learning. And let's take an example. Let's consider this concrete state, and let's convert it into an abstract state by looking at room 1. So for room 1, the unary predicates satisfied for room 1 are robot, at, and room, and this constitutes the role for room 1. Similarly, I've computed the roles for the other objects, which is room 2, room 3, the gold bar, everything included. And to convert a concrete state into an abstract state, what we do is that we replace every object in every predicate by its corresponding role. And that forms the set of predicates for an abstract state. And notice that information about the object names disappears in the abstract state. Another problem that arises is providing truth valuations to predicates in an abstract state, because relationships become imprecise. For example, link room 1, room 2 in red corresponds to link R1, R2 in the abstract state. However, room 2 has two different objects. A role 2 is represented by two different objects, which is room 2 and room 3, out of which only room 1 and room 2 is true. So we use three-valued logic, where for values, predicates which satisfy some relations but not all, we represent the truth value of half, which says unknown. Once we have the abstract state representation, which does not utilize the action models, the next step is to making them model agnostic. So for this, we define a network input interface using the abstract state representation, and we can use that to train neural networks. The way we do this is we take the abstract state and we convert it into a vector representation, which is then fed into the neural network. And at this point, there is no use of the action models. For the second step for achieving model agnostic behavior is we propose a domain independent network paradigm, wherein the network architecture does not require any information about action models. For this work, we define two different networks. The action network, which predicts the action and instantiation hints and can be used for policy-based search, as well as a plan length network, which predicts the total number of steps to the goal and can be used in heuristic search. Uh, One important properties when using the outputs of these two networks is that planning with GHNs is sound and complete when the underlying algorithms are sound and complete. So we do not alter the properties of the underlying algorithms. So with that framework or machinery in place, now we look at how we make learning heuristics data efficient. So we use leapfrogging, which is a hands-free approach for learning heuristics or policies. An important characteristic of leapfrogging is that there is no external training data needed, only access to a problem generator. And we show that it works with any learning approach. So here's how leapfrogging works. It's an iterative approach. So at the first iteration, we have access to a problem generator, and we use a problem generator to generate a problem set. Now, for the first iteration, the problems are so small that even blind search can be used to solve them quickly. And this forms training data. Using this training data, we can now learn a neural network. So for the next iteration, we use the problem generator to generate slightly larger problems than that of iteration one. Now, for these slightly large problems, blind search might be infeasible. But however, we learned a generalized heuristic network in the previous iteration, which has some generalization capabilities. And we can use that to solve this relatively quickly and generate new training data. And using this new training data, we can learn a new improved GHN. So the next generation of GHNs has better generalization capabilities than the previous generation. In this way, we can continue doing this until we reach a desired level of generalizability. So this shows that GHNs can be used for effective meta-learning in relational domains in the sense that we are model agnostic. So the meta-learning technique can be used anywhere. Since we are generalizable, leapfrogging can be used for efficient few-shot learning. I'll now move on to discussing some of the results that we obtained when we tested our approach on a variety of domains. For the empirical setup, we used 13 benchmark domains from the international planning competition. To give a feel of the problem sizes in the training and test set to showcase the transfer abilities, the training data are usually composed of small problems. For example, for Spanner, the problem sizes had up to 441,000 states, whereas the test data composed of much larger problems. For the same domain Spanner, we had problems which contained 100 million plus states in the test data. For our planning setup, which actually evaluates the quality of the learned heuristic, we found that there are no perfect baselines because all baselines used extra information in the form of symbolic action models to compute the heuristic value. We had 6 different baselines, 2 of which were optimized C++ based competition winners. And the others were heuristic search combinations with different heuristics and search algorithms in Pyperplan, which was the same platform on which our approach was implemented. For our meta-learning setup to showcase few-shot learning, we trained 2 different GHNs, one which used training data generated by an off-the-shelf solver, and then we did 3 iterations of leapfrogging using the problem generator with the method that we discussed. Our results show that GHNs are competitive with the baselines, even though they do not use any information about the action models to come up with the heuristic estimates, indicating that they do learn structure of the solutions. We significantly outperform comparable baselines of Pyperplan in both the time required to compute a solution and also the effort expended. Uh, our Python implementation expends fewer effort than competition planners, but cannot solve them faster. And leapfrogging attempts the same performance as GHNs trained without leapfrogging. So the first set of results show how GHNs can be used as an effective model-agnostic few-shot learning technique in relational settings. So for this plot, the x-axis represents the bins, the problem bins, where B plus, the last bin, does not contain any problems that or contains problems that are larger than any problems seen in the training set for any GHN network. Uh, the top plots represent the average nodes expanded, which is a factor of the average effort, and the bottom plot talks about the average number of problems solved. GHN no-leap is the configuration, or the dashed line is the configuration which used training data generated externally, whereas GHN leap 0, 1, and 2 are the ones which use leapfrogging. So as the iterations improve, as we can see, we move from leap 0 to leap 1 to leap 2, we can see that the total number of problems solved in B+, which indicates the generalization capabilities to tasks which are not in the training set, we see that it increases for the later leapfrogging iterations, eventually converging or being higher than the GHN no-leap, which used externally generated training data. We also see that as the generalization capabilities increase across the leapfrogging iterations, the amount of effort expended starts reducing across all the bins. So for example, for GHN leap 0 and bin B0, which is the first bin, we see that the effort expended in terms of the nodes expanded is lesser for GHN leap 2 or leap 1 than leap 0, indicating the few short learning capabilities because the next set is actually solved much faster than using the previous GHN network. So model-agnostic GHNs are comparable to model-based heuristics. In these plots, the top plots represent the effort expended, whereas the bottom ones represent the time taken. In general, taller bars on the left are better. Our approach is the one in orange, and we can see that despite not using action models, GHNs are competitive with the baselines. So for example, in the highlighted block score plot, we can see that the orange bar solves 100 problems in the first bin itself, whereas for the time taken, it solves almost 100% of the problems. And this trend continues throughout the domains, and there are more domains available in the paper. However, GHNs were not able to compete on a few domains. There were two domains which are highlighted over here, one of which is logistics, where GHNs weren't able to perform. We analyzed this and we found that the abstraction technique that we used is not suitable for logistics because it only changes, most of the actions only change binary predicates. And as well as the training data was generating diverse plans because the plans were loosely coupled. For Ferry, the problems were really small. And that's when factors like network inference and overhead from solving the network, when the number of nodes expanded is relatively the same, starts making a big difference because our inference procedure is pretty slow. Not to say, but we do outperform Pyperplan baselines in the time required, where Pyperplan takes a lot longer to solve a lot of the problems for many of the domains, whereas we solve most of the problems in the first bin itself. We also solve most problems expanding far fewer nodes than the baseline, which is evident in the circles highlighted by blue. And this is a trend that follows across different domains. To compare with optimized C++ planners, we are competitive. We solve the same number of problems within the given time limit. However, we cannot solve problems faster than the competition planners at the moment. However, this is not to say that we cannot outperform them. Indeed, on some domains like Spanner, we do outperform FD. Now, Spanner is a special domain because it was explicitly written to not perform well with heuristics used by these competition winners or the C++ planners. And on analysis, we showed that even if we use the C++ planners to generate training data, we could still outperform them, indicating that GHNs can learn knowledge that is orthogonal to the training data source. So in conclusion, we conclude that GHNs can be used to generate effective HGFs, which are generalizable, and they can be used to reduce the planning effort. And more importantly, they can also be used as an effective model-agnostic few-shot learning technique when you don't have access to any training data. Thank you, guys. And the full paper link, which also appears in the main track of AAAI, is found in the QR code, and I'll be happy to take any questions.